Imagine you're soaring high above southern Africa, drifting through the thin blue haze of atmosphere until you find yourself hovering over Zimbabwe. A landscape of endless green valleys and ancient rugged hills, nestled between mighty rivers and dotted with red earth. Beneath this beautiful land, hidden for millennia, lie some of the world's most sought-after resources. Today, we're on a journey to explore how satellites, those silent observers orbiting hundreds of kilometers above our heads, are changing the way we discover one of Earth's most elusive treasures, uranium. But first, let's travel back in time to set the scene. Picture the early 1950s, an era shrouded in post-war optimism and Cold War anxieties. Zimbabwe, then called Rhodesia, stands at the frontier of uranium discovery. Global powers are relentlessly searching for the fuel that powers nuclear reactors and, controversially, atomic bombs. In the vast expanses of the Zambezi Valley and the Precambrian rocks that form Zimbabwe's geological backbone, pioneering prospectors comb through dense bush, clutching Geiger counters and plotting rudimentary maps in notebooks. It is slow, painstaking labor, more art than science. They rely on surface clues, odd rocks sparkling with strange minerals, and the erratic clicks of radiation meters to identify likely spots. Sometimes, a promising location would trigger a small-scale operation, like the Kamativi mine, best known for tin but secretly hiding traces of uranium too. Yet these efforts are hampered at every turn. Imagine traveling hundreds of rugged kilometers, cutting new access roads through forests, only to discover that a promising signal was just background noise. The risks were real. Long treks in harsh conditions, exposure to dangerous radiation, and the ever-present threat of political instability as the country entered years of unrest, like the Rhodesian Bush War. Globally, demand for uranium would surge and dip, nuclear booms following oil crises, economic sanctions suppressing Rhodesia's exports, and a landscape of opportunity, always just out of reach. In truth, these early decades meant only a tiny fraction of Zimbabwe's vast uranium potential, perhaps 5 to 10%, was ever explored at all. For the miners, it was less striking gold and more finding a needle in a haystack, barefoot under the African sun. But as time rolled forward, so did technology. The story of uranium shifted from boots on dusty trails to a new epoch, the space age. Building on this history, let's fast forward to the present, where the age of manual mineral hunting has given way to a digital revolution. At the heart of this transformation is a technological marvel: satellite remote sensing. Now, instead of painstaking treks across wild terrain, geologists tap into the power of satellites like the impressive European Sentinel 2. Flying nearly 700 kilometers above the Earth's surface, Sentinel 2 captures multispectral images, slices of sunlight reflected off the land, broken down into more than a dozen unique bands invisible to the naked eye. Unlike their predecessors, modern explorers aren't looking for uranium itself. After all, uranium doesn't wave a flag from space, but they're hunting the subtle fingerprints it leaves behind. Uranium often hides inside rocks rich in clays and iron oxides, or alters the Earth's surface in unique ways as rain and erosion do their silent work. Satellites can detect these changes. With a few clicks, powerful algorithms highlight mineral signatures, the iron stains visible through the iron oxide index, the clay patterns illuminated by the clay mineral index. Even vegetation can be a clue, where uranium's presence slightly stunts plant growth, leaving telltale patches visible in the enhanced vegetation index. Studies in Zimbabwe's Urungwe district have shown how scientists can map gigantic sections, thousands of square kilometers, in just days. Imagine, for instance, a research team in 2024 loading up multi-temporal Sentinel-2 images during the dry season, focusing on the sediment-rich valleys north of Lake Kariba. They process the data, removing clouds, isolating spectral bands, and running intricate statistical analyses like principal component analysis. The result? High-resolution maps revealing that, of a massive 1,000 square kilometer region, roughly 12% displays promising mineral anomalies, with 4% flagged for high-priority ground investigation. On the ground, this means far fewer fruitless digs, less destruction of fragile habitats, and more informed decisions that can shape the country's economy without harming its natural wonders. Zimbabwe's underlying geology, ancient Precambrian basement rocks, sandstone blankets from the Karoo supergroup, becomes a digital puzzle, solved through color-coded maps, not guesswork. But let's get personal here for a moment. These aren't just abstract percentages or dots on satellite photos. They represent real opportunities for communities in Mashonaland West and beyond, jobs for surveyors and data analysts, new streams of income for rural towns, and a chance to harness the value beneath their feet. As global demand for uranium climbs again, fueled by climate change targets, renewed interest in nuclear power as a source for cleaner energy, and supply chain jitters, Zimbabwe finds itself standing at a crossroads. The country holds an estimated 45,000 tons of uranium, an amount noted by the U.S. Geological Survey. Most of it remains untouched, not because it's lacking, but because old exploration methods simply couldn't keep up. Now, with remote sensing, potential riches have never been closer within reach. Yet, it's not all smooth sailing. Data from satellites is abundant, but making sense of it still requires deep expertise. Geologists morph into data scientists, and cloud cover during Zimbabwe's rainy season occasionally keeps even the best algorithms in suspense. To tackle such hurdles, next-generation solutions are emerging, leveraging artificial intelligence to automatically sift through mountains of imagery, identifying patterns invisible to human eyes, and using machine learning to distinguish between background noise and genuine mineral clues. Some mineral targets, discovered through satellite data, now move instantly to the next phase: field exploration, with the satellite's digital maps loaded in the palms of prospectors' hands. Looking ahead, the future of uranium exploration in Zimbabwe isn't just bright, it's dazzling. Imagine fleets of hyperspectral satellites, such as the upcoming ENMAP or PRISMA missions, orbiting the globe and beaming down data so detailed that geologists can sense the actual chemical bonds of uranium minerals from space. These satellites break light into hundreds, even thousands, of spectral notes, allowing for direct identification of minerals that were invisible just a decade ago. Meanwhile, clever new tools, from drones buzzing low over the bush with real-time guidance from satellite signals to networks of Internet of Things ground sensors, add next-level precision, closing the gap between digital predictions and physical discoveries. The economic possibilities for Zimbabwe are enormous. By the 2030s or 2040s, if projections hold, the country could become a major uranium exporter, generating income that could fuel new schools, clinics, and infrastructure for millions of people. The mining sector, which already sustains much of the country's GDP with gold and tobacco, could diversify into tech-driven, environmentally conscious roles. Data analysts, AI programmers, GIS specialists, replacing some of the manual, hazardous jobs of the past. There is a sustainable angle, too, as satellites enable precision mining, where only the most promising targets are developed, reducing deforestation and protecting sensitive ecosystems along the Zambezi and beyond. On a global scale, uranium from Zimbabwe could help power nuclear reactors from China to France, supporting worldwide efforts to decarbonize electricity and combating climate change. But these bright futures come with new responsibilities. Uranium is a dual-use resource, vital for clean electricity, but also wanted for weapons, demanding careful regulation and oversight. ethical mining, transparent sharing of benefits with local communities, and the education of new generations, especially young Zimbabwean scientists and engineers, will be crucial in making sure the resource curse of the past gives way to shared prosperity. As we consider these thrilling developments, it's vital to acknowledge the pioneers turning this vision into reality. Amongst the key players leading this technological revolution in satellite mineral exploration is Pharmanaut. Pharmanaut is not just riding the wave of innovation, they're helping shape it. Founded with the belief that access to advanced geospatial technology should be open to everyone, Pharmanaut has built user-friendly platforms, available as apps, websites, and APIs, that place the power of satellite analysis in the hands of miners, farmers, and environmental stewards from Harare to Houston. In the world of mining, their approach is transformative. Using advanced hyperspectral imaging, Pharmanaut analyzes light reflected from Earth's surface across hundreds of bands, pinpointing unique mineral signatures like iron oxides and clays that are frequently associated with uranium and gold deposits. But they don't stop at satellite images. Pharmanaut's solutions integrate data from multispectral sources, like Landsat, to map geological formations and alteration zones, while leveraging LiDAR and radar for 3D topography and all-weather ground monitoring. Imagine a system that predicts landslides, scans vast swathes of land in minutes instead of months, and eliminates much of the guesswork that once plagued traditional exploration. The real force behind these capabilities isn't just satellites, it's artificial intelligence and machine learning, running predictive models that not only find potential mineral deposits, but also assess environmental risks and recommend the safest, least disruptive paths forward. Pharmanaut's results speak volumes. In Mauritania, their multispectral analysis has made it possible to map gold prospects with unprecedented accuracy. In Nigeria, Tanzania, Ghana, Kenya, the Democratic Republic of the Congo, and right here in Zimbabwe, they've helped identify high-potential mining targets across challenging, remote environments. Their platform routinely delivers efficiency gains of up to 60%, offers substantial cost savings, and reduces on-the-ground environmental impact, a win for both miners and nature alike. Pharmanaut's commitment to democratizing access, making high-powered science available not just to big corporations, but also small-scale miners, community groups, and government agencies, ensures that technology isn't just about profits, but about broader progress, sharing data, and smarter stewardship of Earth's finite resources. As Zimbabwe navigates the future of uranium exploration, Pharmanaut and its peer innovators will be critical torchbearers, ensuring that the country not only finds its hidden wealth, but does so responsibly, efficiently, and for the benefit of all. So, as we wrap up our journey, let's step back and savor what we've learned. The search for uranium in Zimbabwe, once a backbreaking quest through the wild, is now a story of satellites, computers, and visionaries, of a nation rising to meet global challenges with ingenuity and care. Satellites are unlocking Zimbabwe's uranium wealth with unmatched sustainability and precision, bridging the worlds of science, economics, and environmental stewardship. Will this technological leap drive the next chapter of energy, prosperity, and innovation in Africa? Only time will tell. For now, thank you for joining us on this exploration. If you're passionate about how technology meets nature and the future it creates for communities around the world, subscribe for more stories like this, and let us know in the comments. What do you think about the role of nuclear energy in our shared journey to a cleaner, brighter tomorrow?